start, just want to give a big shout out to our sponsors. It's really cool to have a conference in Sydney that doesn't cost like $900 to attend. So that's obviously not possible without really awesome sponsors, so big thank you to them. Hi, I'm Megan. I am a front-end engineer at JAXA, which is a startup, and I'm here today to talk to you guys about numbers. In general, but also specifically in JavaScript, because if you've ever played around with numbers in JavaScript, you might have noticed they can behave a little weirdly sometimes. So my hope for today is not necessarily that you're going to walk away as experts in numbers. I don't know how you could, because I'm not. But more so that you will be more inspired to dig a little deeper into the bugs that you encounter day to day as developers. So let's go back to basics. Let's go back to Maths 101. What is a number? Well, it's an abstract concept, and numbers, we use them to count, measure, label, and identify. We use them pretty much every day. They're like a pretty ingrained part of our life. And to help us categorize numbers and use them, we can classify them. So we have our natural numbers first up, which is just pretty standard whole positive numbers that we use day to day. We also have integers, which includes our negative numbers, again, still whole. We have rational numbers, so those are numbers that can be expressed as fractions. We have irrational numbers, which are numbers that cannot be expressed as fractions, like pi, or the square root of 2. And we have real numbers, which is a superset of all those previous numbers: natural, integer, rational, irrational. And real numbers are numbers that are on the number line, basically. So from negative infinity through to positive infinity, everything between that is a real number. But we can go beyond that. We also have complex, transcendental, imaginary, infinity and negative infinity, infinitesimals, so real numbers, none of which I know anything about, so we're not going to touch on them today. And just as we can classify numbers in different ways, we can also represent them in different ways. And when I say representation, I merely mean the way that we communicate them. So if we think about the number 8, most people will think of the Arabic numeral 8. We can also represent this as ba in Chinese, or atha in Hindi. Apologies if I've just butchered those pronunciations, feel free to correct me later. But none of these is actually the number 8, right? They're all just symbols that represent the concept of the number 8. And just as we can represent numbers differently in human languages, we can also represent them differently in numeric formats, and specifically in JavaScript. So we have this number, 1,234,567. This is it in base 10, which is what we all know and love, used day to day. We can also represent that number in binary. Octal, which is base 8. Hexadecimal, which is base 16. You'll probably be familiar with that if you've ever done anything with design. For anyone curious, that colour is like a really nice turquoisey blue. And we can also represent numbers in scientific notation. So that just says 1.23 blah 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 times 10 to the power of 6. So we use scientific notation when we're handling really large numbers. And just as a girl has to have her standards, so too does JavaScript. And JavaScript follows the IEEE 754 standard for floating point arithmetic. That is the Institute of Electrical and Electronic Engineers. And this is just basically a specification for how numbers are implemented in JavaScript. It's a really, really long, really dry document. If you're having trouble speaking, I'd recommend it. But it basically explains why 0.1 plus 0.2 does not equal 0.3. So it specifies the implementation of floating point arithmetic, which we'll get to in a moment, and allows us to represent real numbers, so that's between negative infinity and positive infinity, as an approximation to support a trade-off between range and precision. So when I talk about range, it's just the range of numbers that we can represent. In JavaScript, we can safely represent numbers between about negative 9 quadrillion up to positive 9 quadrillion, which is a pretty good set of numbers. And when I talk about precision, I just mean how many decimal places we can accurately represent these numbers too. So we can represent them to 17 decimal places. Like that number, which is what 0.1 plus 0.2 is equal to in JavaScript. So computers have really limited space, right? They're not like infinite amazing machines that everyone kind of really thinks that they are. So we can either have greater range or greater precision. It's one or the other, and we have to make compromises. And everything in computers is just stored in ones and zeros. Computers are really basic. It's all just binary. That says, hello DDD. But we can't have decimal points in binary, can we? Because decimal is from the word deca, which means 10, so that's for base 10. So floating point arithmetic tries to account for that. So let's have a look at that number 1, 2, 3, 4, 5, 6, 7. If we were to represent this number as a binary floating point, it would look like this, which is a little bit ridiculous, and I'm not going to say that out loud because it's quite a mouthful. But what we're looking at here is 64 digits, or 64 bits. And let's break that down. So the first bit represents the sign. This is what a floating point number looks like. The first bit represents the sign, so if it's a 0, it's a positive number, and if it's a 1, it's a negative. The next 11 digits represent the exponent, so basically just tells us where the decimal point goes in that number. And the next 52 bits are for the significand, or the mantissa, and that just tells us what the number, like what the actual digits in the number really are. So let's have a closer look at everyone's favourite JavaScript bug. When I was in primary school, one of my teachers used to always say that calculators are never wrong, it's humans who are wrong. So that's my response to that, Mr. Edwards. So binary can represent integers safely, totally fine, up until about 9 quadrillion and negative 9 quadrillion. But fractions is where we start to scratch our head and get an issue. If you think about a third in base 10, we have to approximate that when we convert it to a decimal, to 0.333 ad infinitum. And just as we all know that 0.33 plus 0.33 plus 0.33 does not equal 1, especially if you've ever tried to do like a 3-column layout in CSS, there's always that pesky little 1% left over. It's a similar problem. So when we convert 0.1 from decimal to its binary representation in JavaScript, it looks like this. And you can kind of see that this 1, 1, 0, 1, 1, 0, 1 kind of keeps on going forever. Again, we are limited by 64 bits, so we have to cut that off. It's a recurring radix, so I said before that binary can't have decimal places, but there is a point right there. That's not a decimal place, it's a radix point. So that point up there is also a radix point, but it's a radix decimal point in our base 10 system, but we just shorten it to a decimal point because we use it all the time. This is just a binary radix point, so similar thing, but different numeric systems. So if we take that number, that binary representation of 0.1, and we convert it back to decimal, we get this. So, not quite right. It should go straight back to 0.1, but because that is just an infinite recurring decimal, or like radix places, we have to kind of round it up, and it causes these bugs when we convert it back later. So hence that problem. But how big of a problem is that really? Let's just put this into perspective for a minute. If I were trying to measure 1 centimetre and I had a margin of error of 0.1604 centimetres, that would be about 0.90 times as long as a glucose molecule. So smaller than a tiny little glucose molecule. All right, still a bit hard to kind of perceive that. Let's go bigger. If I were trying to measure 1 kilometre and I had a margin of error of 0.1604 kilometres, that'd be about 0.21 zeros times as long as the distance from Earth to the Moon. Not big enough. Let's go big, really big. If I were trying to measure 1 light year, and I had a margin of error of 0.1604 light years, it would be about 38.38 centimeters off, which is about the height of a standard bowling pin. That's a fun fact I learned. So in most cases, this degree of accuracy is really not going to be that important. I mean, how many situations have you been in your programming lives where 17 decimal places has mattered? If you're doing a shopping cart, for instance, does your customer need to know how much their cart costs to 17 decimal places or just 2? So we can just round it. We just have ways around that. Moving on. Size really does matter. Let's go back to range. So we've kind of talked about precision a little bit. Let's go back to that range. So when I said earlier that JavaScript can represent numbers between -9 quadrillion and +9 quadrillion, I was actually lying. Sorry. Building trust. If I put in this number 1.7 times 10 to the power of 308, that's a 17 followed by 308 zeros. Pretty big. JavaScript will return that number to me. Okay, cool. Oh. Huh. That's not how I remember maths class. I don't think that if I add 0.1 to that it makes it infinity. But alright. So JavaScript can actually represent really big numbers, but it can't represent them safely. So it has a max value and a min value, and that max value is 1.79, all of those numbers, times 10 to the power of 308. And its minimum value is 5 times 10 to the negative 324, which is 0.324 zeros 5. So that's like the smallest number after 0. So that's a pretty massive number, right? And when we're talking about really big numbers, we have naming conventions. So we have million, billion, trillion, etc. And that convention goes all the way up to a number followed by 303 zeros, which is a centillion. So just by that, like, we know that we've already exceeded the naming convention. We should know that that's like a pretty good range. If you're still not convinced that that's good enough, this number here, 3.28 times 10 to the power of 80, that's the number of particles in the known universe. So if you're dealing with numbers bigger than that, can I have a slice? I want to know what you're doing. Sounds like fun. So yeah, so we've got a pretty good range of numbers, but like I said, we can't represent them all safely. So we have a maximum safe integer, and that is that 9 quadrillion value that I've been going on about. Before ES6, which was released about 3 years ago, this value didn't exist. There wasn't this max safe integer value that you could access. Not really sure what people were doing before that. I wasn't coding, so I have no idea. But sorry for them, I guess. So when we go beyond this maximum safe integer, things start to get a little funny. So let's try to do some arithmetic. Now, max safe integer, it ends in 991, right? Let's add 1. Okay, 992. Well, that makes sense. Why isn't that the max safe integer? Let's add another, oh, that's not right, but okay. All right, we're back on track. Sure. That's, no. Why? Why? So the arithmetic doesn't add up. And this large number problem is actually what inspired this talk. So let me just tell you a little bit about my origin story. So at work one day, I was coding away, and I was trying to render some data on a page, which is like 40% of my job, so I'd like to think I'm pretty good at it. And our database was basically, so for a bit of context, at Jaxter we're building a music database, so you can look up a song and see like all the people who played on it, who performed on it, whatever. So hypothetically, I don't remember which song it was, so let's just say it was Drunk in Love by Beyonce and Jay-Z, which also happens to be one of my favourite karaoke songs. So I was trying to render the credits on the page, and the credits were coming through like this. So we had Beyonce coming through and Jay-Z, they were both coming through, that's great. But look at those IDs. They're the same, which is odd because IDs are supposed to be individual. And what was happening was these numbers are really big. And when JavaScript tried to parse them, they originally were ended in 167 and 168. But as we've seen, those numbers beyond that maximum safe integer get a little funny. So JavaScript was basically saying, okay, well both of these are end in 160 now, sorry. And so I was getting duplicate data on my page. The JavaScript framework that I was using, Ember, was basically saying, hey, I've already got a resource with this ID, so I'm just going to render that again. So I was getting Beyonce through twice, and Jay-Z not at all. Sorry, Jay-Z. So this was a problem, because we were using incremental IDs, and they were really likely to duplicate. But we weren't getting any bugs coming through. They were just kind of a silent error until we noticed that everything on the page was not correct. So our solution was to use UIDs. And UUIDs are universally unique identifiers. They are a 128-bit number. That is a number. And they solve a bunch of problems. The most important one for us is that because they contain non-numeric characters, they had to come through as strings. So we didn't have to worry about like adding them or having them pass through as numbers because they were coming through as strings. So now Beyonce and Jay-Z are both happy, they're both good, and they're both on our website, which is great. So if you're expecting numbers, you need to check them to make sure that they're not larger than the maximum safe integer, because if they are, you're going to have problems. If they are, then get them just passed through as strings. You're not really going to be using IDs for anything except like identifying things. Like you shouldn't be doing any maths with them or anything, so there's no reason why they need to be numeric. They can just be strings. But this just in, and by that I mean it happened about 4 months ago, but I found out about it on Monday. Thanks for that curveball. So someone told me that JavaScript can now handle bigger numbers in the new numeric primitive big int. So this basically means that we can represent numbers, or integers specifically, so whole numbers, beyond that maximum safe integer of about 9 quadrillion. What's also really exciting about this is that it can form the basis for big decimal, which means that eventually we might be able to represent like really specific decimal places. So that's really cool, and they also reference in the documentation about the 0.1 plus 0.2 not equaling 0.3 problem, which is just like the butt of all jokes in JavaScript. So let's take a closer look at that implementation of big int. So we can pass in a number to big int, and it will return a new type. So if we give it 100, it'll return 100n. Which basically just denotes that it is a big integer. We can't pass it decimal places. It'll give us an error. It's not a safe integer. And we also cannot do arithmetic with a big int and a regular number. They both have to be big ints. So let's take another look at this problem, but this time using our amazing new big int. Let's just set a variable of big num, and we'll just convert that max safe integer to a big int. Alright, if we add 1n to it, which again just denotes that that is a big number, or a big int, we'll get 992n at the end. Okay, let's add 2. It's working. Oh my god. Oh my god. It just keeps going. It keeps going and it's accurate, it works, which is really exciting. Caveats, of course, to this, it only accepts integers. It's also only shipped in the V8 engine, which is Chrome, so sorry if you're using Firefox or Safari or any other browsers, you can't do it yet. And it's also very new, so there's not a lot of documentation. It's not even like in the MDN docs anymore yet, so not a lot of documentation for a presentation, perhaps. Sorry. But what I find really exciting about Begin is that it didn't exist 6 months ago. We had no way to handle bigger numbers unless we wanted to use like a third-party library, but then that was complicated and like expensive in terms of performance. So what really excites me about this is that JavaScript is 22 years old, but it's still developing new things and it's still fixing problems that we didn't even think could exist like 20 odd years ago. So it's a really cool like ecosystem to be a part of. So section 3, preaching to the converted. All right, we know all about numbers. We're not experts, but we know about them. What can we actually do with them? Let's say that we have a number, but we want to convert it to a string. What can we do? We can use the toString method. So I can say, I'm going to give you a number of 100 and I want you to return it to me as a string. And it will. Note that that double dot is not a typo. There's a very subtle like color change. The first dot is blue and the second dot is black. This is something that I also learned putting together this talk, is that JavaScript will read the first like point as a decimal. So you need to like have a couple of ways around it, but you can use a second dot or you can use a space just to invoke the method and actually make it return a string. Or you could just add in a 0.0 if you really want to. But we can also actually pass in an argument to that toString method, which is a base. So let's say we have the number 100 and I want to see what that looks like in binary. I can do that really easily by just passing in 2 to the toString method. And I will get a string representation of the binary version of 100. And we can do that from 2 through to 36. So base 36, if you had 36 like numeric characters. Beyond that we can't, just because we run out of alphanumeric characters, so 0 through to 9 and A through to Z. If you were doing like maths on paper, you could definitely go further than that and have like base 70. You just need to have like an agreed upon set of symbols to use. So let's go the other way. If we want to convert a string to a number, we've got a bunch of options available to us. We can use number and pass an argument of string. So if I pass a string 100, I get 100 in return. Fairly straightforward. But this is a strict method, so we can't pass any non-numeric characters. Otherwise it will just return that it is not a number. We can also use the unary positive operator. So we can just do a plus sign and then a string and it will return a number. But again, this is a strict method, so we can't put any non-numeric characters in. We can also use the unary negative operator, which is exactly the same as the positive unary operator, except it does it negative, so it will swap the symbol or the sign. So minus outside of minus 100 will return positive 100, and minus outside of positive 100 will return negative 100. And that's also strict, so you can't pass any non-numeric things. But let's say we don't want it to be super strict, right? We know that there's going to be like alpha characters in there, like there's going to be words or whatever. We could use parseInt, which will accept an argument as string. Pretty straightforward. We put in a string of 100 and it returns 100 as a number. It will not return any decimal places. It's not strict, so as long as your numeric characters are at the beginning of the string, it will return the number. otherwise it will return nan. Parseint can also accept a second argument of radix. So if we know that we have a binary number and we pass in a radix of 2, it will return 255, which is like the decimal representation of 1111111. Yes. Or we could do 16, so if that's in hexadecimal, 0xFF will return 255. We can, if we want to use decimal places, we can use parsefloat, which will return at decimal places. Lovely. Again, if you have the non-numeric characters at the beginning, it will return nan, but if they are if your numeric character is at the beginning, it will return a number. So let's have a look at that number object. It has a bunch of properties, some of which we've already had a look at. So max safe integer, max value, min value, and min safe integer. I read that wrong, I'm sorry. We've also got a bunch of others. So we have epsilon, which represents the difference between 1 and the smallest floating point number greater than 1. And that's that. Inside of the number object, we also have nan. So if you ever feel like you need to access nan and you want to write 7 extra characters to get it, you can just write number.nan. It's revolutionary. Another one that's not going to save you any time typing. Number.positive infinity will return infinity, and negative infinity will return negative infinity. More methods. Methods. So things that we can actually compute. So you might know that nan does not equal nan. People like to joke about this as well. But it's actually a really good thing because we want nan to propagate errors. If we're trying to do some arithmetic in our code and two things are actually strings and they might equal each other, if two things are strings and we try to add them together or whatever and they end up being nan and they both equal each other and it's going to give us true, that's not what we want, right? We want numbers. So to check if something is nan, we can use number is nan and pass in nan, and it will give us true. Anything else will not. We've also got is finite. So 1 is finite, will return true. Hopefully this surprises no one. Infinity is not finite. Shocking. We've also got is safe integer. Anything beyond that max safe integer will return false. So you could use the is safe integer method as like a check for when you're receiving IDs, just to make sure that nothing is too big, and that will give you like a flag straight away, so it won't be a silent bug. We've also got parsefloat and parseint, so we've already covered those. Now let's get mathematical. Let's have a look inside the maths object. So again, we've got a bunch of properties. These ones I don't know anything about, so I'm going to read off my notes. I'm sorry, that's very unprofessional. Math.e will return Euler's constant, which is the base of the natural logarithm. If that means anything to you. We've got ln2, which will return the natural logarithm of 2. ln10 will return the natural logarithm of 10. Log 2e will return the base 2 logarithm of e. There's lots of stuff in here about logarithms, I'm sorry. Log 10e will return the base 10 logarithm of e. Pi, finally something I know, will return pi. We've also got square root of 1 underscore 2, which will return the square root of 1/2, and square root 2, which will return the square root of 2. Not a mathematician, so I don't know the significance of any of these, just putting them on here. And we've also got a bunch of methods in our maths object, 35 of them to be precise. I know 7 of them. There's lots of stuff in there about like sine, cosine, tan, etc. And more stuff about logarithms if you're interested. So I'm just going to go through these 7 because I don't know any of the others. In the next talk, Daisy is going to very briefly touch on sine, and she's going to show you a sine wave. And that's enough sine for today. So math.abs will not give you a 6-pack. It will just return. It'll just return the absolute value of a number. So that's just if we're thinking about the number line. It just basically returns how many units away from 0 that number is. So -1 is just 1 unit away from 0, so it will return 1. We have math.ceil, which will round a decimal place up. We have math.floor, which will round it down. And we also have just round, which will round it whichever way it should go, whether it's up or down, whatever it's closest. We also have math.pow, so that will return 2 to the power of 3, so the first argument to the power of the second argument, which is 8 in this case. We have math.random, which will return a random value between 0 and 1. And we have math.square root, which will return the square root of whatever value you pass in. So JS has some quirks with numbers, and there's lots of cool stuff that you can do, and lots more beyond the limit of the time of this talk. I could have gone a lot deeper, but then we could have been here for like days. But the important thing to remember is that context is everything. How you're using your numbers in JavaScript will affect what you can do with them. So understanding the limitations of how they work will help you understand any bugs that you encounter and help you fix them. So if your numbers are meaningless, use strings. If you're handling, say, currency, for instance, round it to 2 decimal places. You don't need anything further. So hopefully, when you approach any mathematical problems in JavaScript, you will be like this good boy, able to figure it out very successfully. I really like dogs, so it was very hard for me to not put a lot of dogs in here, but I didn't want to overwhelm you all. But yeah, that's it, so thank you.